All right, ladies and gentlemen, class recording for today has started. So, let's take a look and let's start off on this page here that says conceptual physics practice page dealing with friction. So, in a situation that is appropriate for the next couple of days, question number 1 says, a crate filled with delicious junk food. Substitute whatever kind of junk food you want. You can pretend it's candy because it's like Halloween, you know, rest on a horizontal floor. Only gravity and the support force from the floor act on it as shown by the vectors for weight and normal force. Remember we talked about that force that comes from the floor, we call that a normal force because it's perpendicular to the surface that causes it. So, to answer this question, the net force on the crate is 0 or greater than 0? 0. Say again? 0. Alright? What is our evidence that the net force is 0? Very good.
The weight and the normal force are acting.
Okay, what is our evidence for that? How do we know that that is in fact true? You want somebody else to pick it up? It's good. How do you know that? Sammy, go ahead. The box is not moving, right? And that means its acceleration is what? 0. And if its acceleration is 0, what does the net force have to be? 0. Good. I know, we're a little tired this morning. And, you know.
Is that drinking water tasty drink?
Yeah. I mean, I don't drink out of it, but not because I think it's dangerous. I just go to the drinking fountain. All right. Question number 2. Okay. Apparently, are we going to let it slide down? Oh, there we go. Okay. All right. So it says a slight pull, which is labeled P, is exerted on the crate, but not enough to move it. So it's a heavy crate. Guy pulls on it, and nothing happens. There's a friction force, which is labeled as F. How big is that friction force compared to P? Eric. Equal to P. That is the correct answer. All right? And Eric, that means that net force on the crate is now 0. Okay? We have 4 forces now, but they are canceling each other out. We're going to get to that today. So for number 2, N, P, W, and F. F is kind of like on the ground right there because it's friction, so they wanted to throw that in. All right. So, pull P is increased, and the crate now starts to move. Okay? However, this isn't at the moment that the crate starts to move. Notice it says here, after it's already moving, it is pulled so that it moves with a constant velocity across the floor. So not at the moment that it starts moving, but as it's pulled across the floor with constant velocity. Friction, less than, equal to, or greater than P? Right. If it says constant velocity, that means that friction has to be equal to P. Right? Because, Joanna, right? Constant velocity means acceleration is 0 or more than 0. If the velocity is constant, what's true about the acceleration? Well, the velocity is not changing. There's no acceleration. So for 3b, right, constant velocity means acceleration is 0. Right? Does that make sense? And if acceleration is 0 for 3c, that means that the net force is, if acceleration is 0, what has to be true about net force? It has to be 0 as well, right? So the net force in the crate is equal to 0. Okay? Good with those? All right, let's take a look now at question number 4. So it says, pull P is further increased and is now greater than friction. If pull P is greater than friction, the net force on the crate is less than, equal to, or greater than 0. It is now greater than 0. So the net force is greater than 0 for 4A. Net force acts to the right. So acceleration acts towards the right because net force causes acceleration. Good there with those two? Okay. This one here for number 5 kind of jumps back and relates a little bit more to question number 3. It doesn't relate to this picture. Okay? So, if the pulling force P is 150 newtons and the crate doesn't move, what is the magnitude of F? Has to be 150, right? Because if the crate doesn't move, what does the net force have to be? 0. Here's a tough one. If the pulling force P is 200 newtons and the crate doesn't move, what is the magnitude of F? 200. All right, for number 7, if the force of sliding friction, so friction that's acting on the sliding box, is 250, what force is necessary to keep the crate sliding at a constant velocity? 250. Even though it's currently moving now, right? So the question number 7 is different than 5 and 6 because it wasn't moving in 5 and 6, now it is. What does it tell you about how it's moving in number 7? Constant velocity, right? So even though it's moving, if it's moving with a constant velocity, the net force is still 0. Okay? All right, good there? Then, question number 7 and question number 8 relate to each other. So if the mass of the crate is 50 kilograms, right, here, let me do this. Go ahead, Jack, finish filling that up. Not good.
It's like plastic.
That might be the plastic bottle that it's in and throwing it out there. You could just go to the water pump.
That's right. Go get it.
You didn't even ask. You may go to the water pump. Yes.
I need to take that fast.
It's right by the door right there. Just grab it on the way by. So, all right. See, this is what happens when. So it's the bottle, is what you're telling me?
Just like small things. You just want to have a full of paint.
Maybe the fact you were throwing it around the room made it happen. All right. So let's finish up here this sheet for question number 8. Question number 8 relates to question number 4. So we said in question number 4, P is increased and is now greater than friction. So we said that the net force is greater than 0, and then if the net force acts to the right, acceleration is to the right. So for 8, if the mass of the crate is 50 kilograms and sliding friction is 250 newtons, what is the acceleration of crate when the pulling force is 250? Well, that question hopefully is pretty easy to answer, right? What's the acceleration going to be in that case?
5. Oh.
Do we understand why that's 0? Okay, well, so this is asking us about acceleration, right? Okay, so Newton's second law tells us about acceleration, yes? And we said that acceleration depends on two things. What are the two things acceleration depends on? Net force, right? So here is the equation that relates net force, mass, and acceleration. In this case here, we already said, what do we know is true about W and N here? Their net force is 0, so they cancel each other out. But in this case, it says that P is greater than F, right? So in this case, we can change the top of that equation to look like this. Does that make sense? Because does it really make sense, or did you just say that? Oh, okay. But what do we know about F compared to P in this problem? Well, they cancel each other out in the first part, right? Sorry, more generally. We're adding them together, but which direction does F go in relation to P? F goes to the, as opposed to left and right. Are they in the same direction? No. So that means one of them has to be what? Does that make sense? What I just did right there? Are you okay with the negative sign I threw?
Yeah.
Okay. We distinguish direction with the negative sign, right? So if F's going in the opposite direction, we make that one negative. But we're still adding them together, right? So in this case, for the first part, if friction is 250, we'll put 250 in here, but it's negative 250. If P is 250, if we have 250 plus negative 250, what do we have on the top of that equation? 0, and that means that the acceleration is 0 regardless of what the mass is, right? But for this problem, right, now it tells us that the pulling force is 300. So we have A is equal to P plus negative F over M. 300 goes here, but the sliding friction is only 250. So we're going to plug 250 in for F, but it's negative 250 because it's in the opposite direction. It told us that the mass of the crate is 50. So what is the acceleration in that situation going to be? Okay. Yeah. And then for this one, does it make sense that the acceleration is 5 meters per second? You see where that comes from? All right. Good? Okay. These are all conceptual things. Let's start putting some definitions on our conceptual things, and let's talk about friction. So go ahead and grab your outline, and let's discuss. Okay? So today, I want to introduce 3 terms to you. Static friction, maximum static friction, and then either sliding or kinetic friction. Those 2 terms are interchangeable. We use them depending on which book we have. Okay? So, to review, the concept of net force, right? Net force is the combined effect of more than one force acting on the object, or the sum of the forces. Okay? Now, just because we're adding doesn't mean we always end up with bigger numbers for net force, right? We have to take into account direction and all that fun stuff. But something that we have to keep in mind, the motion of an object will only change if the net force is not 0. That last statement, the motion of an object will only change if the net force is not 0, is a summary of what concept that we've already introduced so far in this unit. Sorry, right, then we'll talk. sorry, net force. Two ways that we can signify net force, right? Sometimes we just go F net, right? But then we can also use which notation to represent the sigma, right? The sigma F. Either one of those two we can use for net force. What do you think about these majestic mountains down here at the bottom? Is it peaceful? I've made them in the past. This was a design on like a really old PowerPoint, and I liked it, so I just keep saving it as a new version. But it keeps these mountains down at the bottom, so yeah, I do. I think that's maybe, or maybe it's just like the sun coming up or something. I don't know. I don't know. I'm just making stuff up right now. So, all right, hold on a second. Let me get. All right, so this last statement. The motion of an object will only change if the net force is not zero. That's the gist of what concept that we've talked about so far. That's inertia, right? An object will not change what it's doing if its net force is not zero, right? This is the gist of inertia. Okay? Good there. All right. So let's talk. I'm going to skip Roman numeral number 2, letter A. All right, and let's drop it down to B, and let's talk about this guy right here. Okay. So this guy decides that it's time to get himself in shape, so he buys the flexorciser. Okay. Now, the commercial's great. It says they'll drop it off at your house, but little did he know when he ordered it, that they just like drop it in your driveway. Like they don't actually take it into the house. So he apparently doesn't have like a dolly or a cart or anything, so he just lassos it and like says, here we go, right? So yeah. So he applies a force. Oh, not what I wanted. So he applies a force to this box, but it doesn't move. Why? Right. Static friction, or let's go more generally speaking, right? If you apply a force to that box and nothing happens, what else does there have to be? Got somebody else to take it from me? Join it, go ahead. Well, let's go more generally, right? Friction is a specific type of what? Force. So if you apply a force to this box and nothing happens, there has to be another force, right? Which way does that force have to be going? The opposite way. How big does it have to be? No. The same. Right? So, two things. Do we understand why it has to be the same?
Why can't it be less?
Well, if it was less,
Or more. Why can't it be more?
if it was more, if there was more force this way, right? Would there be a net force? Yeah. Hold on a second, Frank. We'll get there. So, Chris, do you understand why it can't be bigger? Okay. Another wrong answer. Okay. Another incorrect or not describing the situation. A lot of people will say that it doesn't move because the box is too heavy. All right? Not true. Too heavy is describing what characteristic or what property of the box. That could be, or a lot of times we could also talk about how much mass it has, right? Does mass determine if something moves? No. Forces determine if something moves. Mass helps determine how much it moves, but not if it will move. All right? Does that make sense? Okay, so if this man applies force to the box, but it doesn't move, why? Because there has to be another force acting on the object. And we said it has to be how big? Equal, and in which direction? Opposite. And we refer to that force as static friction. Right? Static friction is a frictional force that prevents an object from moving when a force is applied to it. And Joe, because I heard you kind of mumble it there, this is static friction is an example of what? You kind of meant, you said a word there when you were going through. This is equilibrium, right? Net force is 0, acceleration is 0. Okay? The static friction acts on stuff that prevents it from moving. Okay? All right. So, natural response in this situation. You pull on something, it doesn't go anywhere. What's going to be your natural response? Pull harder. So, man applies a larger force. Look, blue got longer, right? But still nothing happens. Why? Static friction. If blue gets longer, but nothing still happens, what had to happen to red? It had to get longer too, right? Static friction is not a constant force. SF, right? F for force, SF for static friction, changes with the applied force to keep net force equal to 0. Okay? Good there? So let's take a look at that graph that you guys have down there at the bottom of the page. Now, your graph is a little bit more detailed than mine because I couldn't find the right picture yesterday when I was making this. So, on the left-hand side, it says frictional force. That's what's being measured on the y-axis. And on the x-axis is applied force. Yes? Okay? So we have frictional force here on the x-axis, applied force on the y-axis. Okay? Now, you'll see here, this is labeled FS max, and then underneath you guys have some, like a weird symbol there. Just cross that little symbol out there, okay? There's a little, it's like, looks like a U, but it has a tail on it. Just get rid of that. Good. Right? Yeah, get rid of the gibberish underneath FS max, and get rid of the gibberish next to FK. Okay? Just leave FK and leave FS max, but get rid of the gibberish that's next to it and underneath it. Yeah, but when we get to chemistry, not now. So. I'm pretty sure you guys have already learned about physical and chemical changes, though. I mean, let's be serious. Right?
That's like
so,
what the other classes do.
Yeah, because they're doing chemistry first. So.
We're going to do that last?
Yep.
What's the hardest unit we're going to do?
The most important unit is the one we're doing right now. All right. Pink. The pink section that I highlighted right there. You can see underneath here that pink section is labeled as the static region. So if we refer to something as static, what does that mean, or what is that describing? Stationary, or it's more generally not changing, right? So we have an upward sloping line. What do you know about the ordered pairs that make up this upward sloping line? What's happening to the x values of those ordered pairs? They're increasing. What's happening to the y value of those ordered pairs? They're increasing as well, right? So, if the x values are representing the applied force, how much we're pulling on the box, and the y values are representing the frictional force, how much friction is acting on the box, as we apply more and more and more force, friction gets bigger and bigger and bigger. And that means those two forces cancel each other out, and we're left with a net force equal to 0. Okay? Good there. Now, does that continue to happen indefinitely? Or continuously? No. Two reasons you can answer that question. One, well, if you look at the graph, eventually that sloping part of the line ends. Right? But two, if static friction just kept getting bigger or smaller to match any force that you could apply to something, what would we see? Nothing. Right? Alec, the net force would always be what? 0. And if the net force is always 0, nothing would ever change. That clearly doesn't happen. So there has to be a value. And that value here is represented by this notation, right? Fs max. Or probably to be consistent, because it came from a different book, we should probably call it S or SF max, right? That's an important value because that's the maximum static friction. Okay? That's the highest level that static friction can become. So if we want something to move, how much force are we going to have to apply? More than maximum static friction. Because up until that point, static friction just keeps matching us. But if that's the biggest static friction can go, if we go higher than that, now we have what? Well, movement is a little too generic. If we apply a force bigger than maximum static friction, what's true about the net force on the box? Greater than 0. And if net force is greater than 0, what happens? Acceleration. Good. All right? So, here's a big hossy guy. All right? How do I know? He's got a hard hat and a back brace. Only hosses wear hard hats and back braces. So, hossy guy applies a huge force to the box and it starts to move. Why? Yes, he's jacked, right? That's required for applying a huge force to the box, right? But why, so Betty, why does a box start to move?
Because it's higher than the force is higher than
Maximum static friction, right? Or more generally, we have a force bigger in one direction than the other direction, right? So here, the man's force, you guys have a picture of this on the back side, right? The man's force is greater than the maximum static friction. So we end up with unbalanced forces or a net force, and a change in motion occurs. In this case, it speeds up, right? So on the back of the outline, right? The man's force is greater than the maximum static friction force. Yes? Yeah.
Do we know the value of the maximum static friction?
The maximum static friction is going to depend on a couple of things, okay? And that gibberish that I had you scribble out, we're going to talk about it more conceptually. That's when you get into it. But it depends on the object itself, right? A heavier object, a heavier box is going to have a greater maximum static friction. But it also depends on the surface that object is on, right? A rough surface is going to have a greater maximum static friction than the smoother surface. So do we know? Yes, we can measure that. You're not going to be responsible for measuring that, though. Okay. All right? So, now, if we apply a force greater than maximum static friction, what happens? It accelerates, and now it starts to move. Okay? Do frictional forces act on moving objects?
Yes.
Yes, they do. But it's not static friction anymore. Now we change it into kinetic friction. All right? I'm assuming you guys have heard this word before, kinetic, right? Okay? Probably in the context of kinetic energy. All right? Kinetic energy is energy that deals with what? Or energy because of what? Movement. So now, when we go from static, which means still or not changing, to kinetic, now we're talking about friction that's acting on a moving object. Okay? Notice the change in the frictional force, right? First, which one's the frictional force in this picture? The red arrow. 2 reasons, right? 1, it's smaller than blue, but 2, which way is it acting? Opposite of the way that we're moving, right? When I go from static friction, or the box not moving, to kinetic friction now that it is moving, watch what happens to my friction arrow. Ready? Okay. 1, it changed colors, but 2, what happened to the magnitude of that force? Got smaller, right? So, kinetic friction, or sliding friction, is a frictional force that acts against a moving object in order to slow it down. Kinetic friction is a frictional force that acts against a moving object in order to slow it down. Yes, Jim? Probably not for a couple weeks. So we got like 2 more kind of big ideas to cover. So yeah.
This test is going to be massive.
It's kind of a big test, yeah. So,
Is it like any place?
I don't know about that, but yeah. Easy. Focus here. Kinetic friction. All right. Question. Is it harder to get something to start moving or to keep it moving once it's already in motion? Have you ever tried to move like a couch across the carpeted floor in your living room? Anybody ever? Is it harder to get it to start going or once it's already going? It's harder to get it to start going, right? If we head back to this picture, right, that shows the graph, okay? During the pink section, the frictional force increases as the applied force increases. And we label that as the static region. But then it shifts to here. And notice this is labeled as the kinetic region. Right? What are you seeing about the frictional force in the kinetic region versus the static region? 2 things that I hope you notice. Jack, what's one thing? It stays the same. So once an object is moving, it experiences the same frictional force. What's the other thing that you might notice about the friction in the kinetic region versus the static region? It's not changing, right? So it stays the same. So that's one thing. Okay. What about the value of the friction in the kinetic region versus this value? It's lower. Once an object starts moving, it experiences less friction. So, if we have to apply this much friction to get it to start moving, but then once it's already moving, we only have to apply this much friction, it's easier. All right? So, oh, duh, there's that picture too, right? So, kinetic friction is smaller than the maximum static friction if we're talking about the same object on the same surface, right? If I take this book and push it across the table, right? I overcome its maximum static friction, it goes to kinetic friction. The kinetic friction there, right, is smaller than, like, if we talk about like the kinetic friction on a car or something like that, right? So keep in mind that that statement is true if we're talking about the same surface and the same object. Okay, so, right, the big horsey guy that's in the picture, that was in the picture before, he's not there anymore. So what force went away? His push, right? So question. Sorry. Right? If his push went away, right? Pushes are contact forces. No contact means no force. So that blue one went away. The only force left on something is the kinetic friction. So, does kinetic friction act on things as they slide across the floor? Yeah, because eventually what happens to that object as it slides across the floor? Stops, right? So here's the question. Once it stops, is this force still there? No. Right? I suppose you could rationalize that in 2 ways. One, if it's kinetic friction, kinetic relates to movement, so that wouldn't apply. But if that force did stay there after the object stopped, what would start happening? Does that make sense? Did everybody hear what Jack said? Said it would start moving backwards, right? This box is moving to the right, and it experiences a force to the left that causes it to negatively accelerate. But if something is already stopped and experiences a force to the left, it's going to start moving to the left. Right? So, once the box stops, does sliding friction still act on it? How do you know? The answer is no. If it did, that box would start moving backwards after it stopped, and that doesn't happen. So, sliding friction or kinetic friction only acts on objects when they are moving. If there is no motion, there is no kinetic friction. Wow, it's almost like what time it was, right? Yeah. Julia, go ahead.
What's number one?
So, number 1 underneath what? Alright, so without motion, there is no kinetic friction. Okay? So, for tonight, make sure you get the quiz done. The quiz doesn't really relate to friction stuff in general, but we did talk a lot about net force and combination of forces, right? So we'll do the top page tomorrow, right? We'll do the top of it tomorrow. So get the quiz done, and then we'll review friction with Roman numeral number 2, letter A, tomorrow in class. Okay?